All right, let's have a look at question 6 though. So question 6, we've just done confidence interval questions. Let's have a look at some hypothesis testing questions. Okay. So we've been told that the standard deviation of the scores obtained in a particular test of mathematical ability is known to be 15. Okay. A school experiments with a new method of teaching which is supposed to increase general quantitative awareness. A group of 99 students are randomly assigned to one of the two classes, with 50 going to the first class where the new method of teaching is taking place, and 49, the remaining 49 students are sent to the second class, same way of teaching, so it's taught in the traditional way. At the end of the year, the two classes are given the same test of mathematical ability, and it's found that the mean of the first class is 116, whereas the mean of the second class is 113. Does this provide enough evidence at the 10% level of significance that the new method leads to a higher mean performance? All right. Let's first of all strip out the fact that we're dealing with tests of mathematical ability and all sorts of stuff like that. Let's just pull out the numbers. We've got two groups. Okay. So let's call them Group A and Group B. So we're told here that Group A are given the new way of teaching, and Group B are obviously given the standard or traditional way of teaching. So okay, Group A, we have 50 students in Group A, so N1 is equal to 50. And if I read down a little bit, it says in the last paragraph of the last sentence of the second paragraph, it says the mean of the first class is 116. So I'm going to say x1 bar is 116. And actually in the top sentence, or the top paragraph, it says that the mean on this particular test is known, the standard deviation on this particular test is known to be 15. Okay, so because we aren't told anything else about standard deviation throughout the rest of the question, we can assume that it's still going to be 15 at the end.
Yeah, that's the thing. I was a bit confused with that.
Yeah, exactly.
It's assuming a lot, especially when you change the whole. Like,
yeah.
You test, you do it in a certain way, and then you change the teaching, and then that doesn't affect it.
Yeah, quite exactly. It doesn't really make sense, right? Yeah. But that's all we've got to go on at the moment. Yeah, so I agree, you think about it logically, it should be that because the test is changing, the standard deviation should also change as well, because you've got different methods of teaching now. But because we aren't told anything else in the question, we have to assume that it's still going to be 15 at the end, because we haven't got anything else to use, and otherwise we can't do the question. Okay, so second group, we've got 49 students. We've got x2 bar is going to be, well, if we read down, it's going to be 113. And we've got sigma 2 is still 15. Okay. Okay, so we need to answer the question. Does this provide significance evidence at the 10% level of significance? Okay, so that's our significance level, 10%. That the new method, in other words, Group A, leads to a higher mean performance. So Group A should have a higher mean on this test than Group B. Okay. So because it's a hypothesis test, where do we always start when we're dealing with hypothesis test questions? Yeah, okay, we can do it that way. No, that's fine. No, absolutely, we can do the tests. So okay, let's do the questions first of all. T. That's great, thanks. Okay, so that's the questions which we need to do. So first of all, do we have N1 and N2 greater than or equal to 30? Yep. Yes, we do. Do we know the population standard deviations for both? I think we can assume that that means the population standard deviation, right? So in which case, I think we're going to go ahead and use the Z distribution. Okay. Now, once again, this is just one way of justifying it. You could absolutely sit there and say, that doesn't really sit right with me. I'm going to use a T distribution on the basis that it's still a sample. Okay, so if you wanted to use a T distribution, you gave a valid reason for doing it, you are totally fine to. I think using the classic way, or the way which I'm kind of, saying it's a good way of trying to argue it, Z distribution is fine. Okay, so if we're going to be using the Z distribution, we don't just worry about degrees of freedom or anything like that. We can just jump straight into the test procedure. So what's the first thing what's the first thing that we need to do when we're doing our hypothesis test? What's the first thing we need to write down? Absolutely. So before you do anything else, it's a hypothesis test. Let's write down our null and our alternative hypothesis. Now just remember, we're only ever talking in this course about means, okay? So because we have two groups, group A and group B, we're not going to be asking the question, is the mean equal to this particular value? Instead, we're looking for difference in the means, okay? So what's our null hypothesis going to be? Good, exactly. There's no difference between them. Yep. So we're saying, okay, the mean of group 1 is exactly the same as the mean of group 2. Okay, so there's no difference between them. That's always going to be the null hypothesis. If you're not sure ever what the null and alternative hypothesis is going to be, null hypothesis is always, it's equal to whatever is stated. Okay, so in this case, if we're looking for difference of means, it's always going to be there's no difference between them. Okay, because at the moment, we're kind of like, well, we haven't got any evidence to suggest that. That's what we're testing against. So what's the alternative hypothesis going to be?
I guess B, the mean of A would be bigger than the mean of B. The way it's written, it says it's strictly higher mean performance. So that's, but it could also be not that because it does. So no, actually, it could be both because it doesn't necessarily mean go higher. I don't know. It's a weird one.
Sean, have you got any ideas?
I think mean 1 is bigger than mean 2 because talking about new method is higher than mean information.
Okay, good, exactly. So a good rule of thumb, and I will try and structure a question very, very similar to this in exams so that you understand where to look. Always look in that last sentence. So where it says, does this provide enough evidence at this level of significance, that, and it's always the bit that comes after the that, after the level of significance bit, that will tell you what the alternative hypothesis needs to be. So in this case it says the new method leads to a higher mean performance. So if this is the group with the new method, so actually I'll just write in here, this is the new method, okay, and this is the old method, just to remind ourselves. What it's literally asking for is we want to establish, is this group got a higher mean than this group? Okay, that's what we want to test against. So mean 1 is higher than mean 2. Does that make sense?
Yeah.
Yep, okay, good. So using this then, the alternative hypothesis should tell us what type of test we're going to be using. So whether it's going to be right, left, or two-tailed. Okay? So if it's mu1 is bigger than mu2, what type of test are we going to be doing? Good. Yeah, we're going to be using the right-tailed test. Yeah. So, okay, let me draw. I'm running out of space a little bit. Let me draw it here. I think is probably the best and most sensible place to put it. So here we go. There's my normal distribution curve. It just needs to be a shape that looks roughly like the normal distribution. At the moment, I'm saying there's no difference between them. So in other words, if there's no difference between them, I'm proposing that they are exactly the same curve as each other. Well, okay, they're centered around the same point. They could obviously have different standard deviations, but in this case they don't. And I want to establish a right tail. So in other words, I want to establish what is the probability, or what is the chances that this particular sample that I've been given ends up in that right extreme, okay, so this right tail, because I literally want to establish that. Now, what is the size of this critical region? That's the region where I'm going to reject the null hypothesis. What's the size of that? 10%, perfect. That's exactly the same as the level of significance. So in other words, there's 10% chance that I just end up rejecting the null hypothesis just because it's there, right? Hence, I have to include 10% of my data in that right tail. Okay, I don't care what's happening in the left tails or the kind of left region. It's just what's the probability that I end up here. Okay? So I guess first of all, let's work out what that critical value is going to be. All right? Now, how could I work out what that critical value is going to be? The value where the region starts. So if you think about it, we're using a t-distribution, right? And because this is just a t-distribution, sorry, not t-distribution, z-distribution, right? Because this is just a z-distribution, we're literally going to be asking the question, well, all right, we want to include 10% of our data up here, okay? Which means that there's 90% of our data up to this point, okay? So if you literally just have a look on our tables, now you could, there's two ways of doing it. You could absolutely use your Z tables, okay? So the Z table's up here, and literally just find the region that corresponds to, well, not 10%, but 90%. Because are you happy our Z tables are cumulative, in other words, from the left, right? So we can't find the upper probabilities, we can only do the lower tail probabilities, okay? So if you look in your tables, look in these kind of big numbers here, all these numbers here, you're looking for 0.9000, or as close as you can to it, okay? But the easier way, I think, of finding those is by actually going to our t-distribution tables. You might say, well, what? Why are you using t instead of z? Well, if you have a look on the bottom of this table, the bottom row, are you happy it's got z star? Okay, on the basis, of course, that we've discussed t-distribution approaches the z-distribution. So actually you're saying, well, okay, above like 1,000, you pretty much just got the z-distribution tables anyway. But the reason why these are slightly easier to use is because the way that the t-distributions are presented are literally in terms of confidence levels and upper tail probabilities at the top, okay? So in this case, I'm looking for a tail probability of 10%. So I just literally need to find 0.10, which is that one there, okay? You see that column there? And therefore, I just go down to the bottom row and I find that comes out as 1.282. It's that quick, right? So 1.282. In other words, any units of standard deviation above 1.282, so if this particular sample, or samples I should say, lie in this particular region, more than 1.282 units of standard deviation from the hypothesized mean, I know I can reject the null hypothesis in favor of the alternative hypothesis. So now, the next job is to look at our sample data and say, okay, what is how many units of standard deviation from the hypothesized mean do I lie, right? Can anybody remember what I call that? So I call it the test. Yeah, test value, that'll do, or test statistic. Statistic, yeah. So there you go, okay? So to calculate the test statistic, I'm literally asking the question, well, how many units of standard deviation do I lie from the mean given this particular sample data? So in order to calculate that, it's a Z distribution. It's nice and straightforward. It's just simply Z is equal to, okay, so first of all, I'm going to do difference in the means. So it's going to be x1 bar, take away x2 bar, minus the difference in the hypothesized difference in the means, so mu1 minus mu2, all divided by the standard error. So square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Right? So let's stick in our values. So x1 bar take away x2 bar is just going to be 3, because 116 take away 113. Mu1 take away mu2? What do you reckon?
So to H, the first hypothesis is the same, so it'd be 0.
Good. So it's always, remember when we do this test, we always assume the null hypothesis is true. So quite literally here, we assume that that must be true. So if the mu1 is equal to mu2, then it means that mu1 take away mu2 is equal to 0. Right? Okay, so in other words, it's going to be 3 take away 0, all divided by the square root of, right, sigma 1 squared, just plug in the values, so it's 15 squared over 50 plus 15 squared over 49, all square rooted. So, over to a calculator. What does that come out as?
0.99.
0.99, okay. Okay, so you can see immediately here that actually 0.99 does not lie in the critical region, right? It lies out here actually. Okay, So 0.99 lies out here. It doesn't lie in the critical region. Therefore, we know immediately where this test is going to go. It's going to go in the favour of we're not going to accept, or we're going to fail to reject the null hypothesis. Okay, in other words, we can't sort of say anything that the null hypothesis is not true, for example. Okay, so that's the direction which the test is going. What's the other thing that we need to do just to be sure, though?
Find the p-value.
Good. I would also find the p-value as well. Yeah, well done. So let's do the p-value. Now just remember, the p-value is the probability of obtaining this sample just by pure chance. Okay. Now in this case, because our tables are cumulative, we have to adjust the definition of a p-value, which is it's not just the probability of obtaining this value, it's this value or a more extreme one. So if it's more extreme, it means lying further away from the hypothesized difference in the means. Okay, so it means lying to the right. So we're literally going to ask the question, what is the probability that z is greater than or equal to 0.99? Now clearly we can't find that directly, so we're going to have to do a 1 minus jobby. So it's going to be 1 minus the probability that z is less than, well, actually just less than is fine, 0.99. Okay? So we can jump over to our tables to do that. So it's going to be 1 minus 0.8389, which is going to be, let's see if I can do this, 0.1611. Yeah, or about 16%. Okay, so that confirms it. Because the probability of obtaining this sample or a more extreme one, so I'll move out the way, is 16%, whereas our significance level, in other words our cutoff level, is just 10%, are you happy that's also more evidence that we should reject, that we should fail to reject the null hypothesis? Okay? So, let's break it down into what we've done then. Let's just to make sure that we've done everything. So first of all, we've done the hypotheses. Next, we've calculated the test statistic. Next, we've calculated the p-value. We've seen where everything lies in relation to the graph. What's left to do?
Summarise.
Good.
Explain if we fail or not. Basically, just to put in words what we've done.
Exactly, yes. We need to put it into words, so we need to conclude. Okay. So remember the conclusion? Break it down into 4 parts. Okay. First of all, describe what the p-values and what the test statistic tells us in relation to our tests. Okay, so let's first of all think about the test statistic. So we can say the test statistic, or test stat for short, is smaller than our critical value. Okay, so it's smaller than the critical value. Now obviously I'm just abbreviating here. So test statistic is smaller than the critical value. If you wanted actual numbers here, you could say, okay, the test statistic was 0.99. That was smaller than our critical value of 1.28. You also need to do this in relation to the p-value. So you can say, okay, the p-value is greater than our significance level, which of course is just alpha. So again, giving values, our p-value came out at 16.11%, and our significance level was 10%. Okay? So if you like, this is the evidence stage of our conclusion. Okay, so we always need to give some numbers to back up our claims. So these are the evidence stage. Test statistic in relation to critical value and p-value in relation to significance level. Then we can actually say, do we reject or fail to reject the null hypothesis? Remember, it's always in terms of null hypothesis. We never say accept. Okay, it's either reject or fail to reject. In this case, what do we say? Yep, fail to reject the null hypothesis. Okay, so that's the next step. We actually say reject or fail to reject. Then the last step is we always say what this means in the context of the question. So if we have a look at the context of the question then, it is talking about whether this new method is better than the old method, basically. Okay, this new method of teaching, is it better than the old method of teaching? Well, actually, in this case, can you see that because we failed to reject the null hypothesis, in other words, we're more inclined to believe this one is true. Of course, we never say anything is true because we're statisticians, but in this case, we failed to reject this. In other words, we don't have any evidence to say that this is not true. Therefore, we can say that actually the mean scores are the same. So actually, the new method of teaching doesn't look to have that much difference to the old method. Is that okay? Okay, so yeah, literally just put that into words. So we say there is not enough evidence Okay, so the way which you word this, you have to word it quite wishy-washy to a certain extent. You can't be precise about this. You kind of have to say, well, based on this and based on that, then there's not enough evidence to suggest that there's difference. Because of course there could be a difference. It's just you can only work with what's in front of you. You can only work with the data in front of you. So I would say there is not enough evidence at the 90% confidence level, or 10% significance level, I should say, that the new method, and again, I wouldn't say the new method is better or worse than the old method. I would say about their test scores. Because of course, it could be the new method is much more entertaining, right? So therefore it could be better. So I would say, again, the new method leads to higher mean test scores than the old method. All right. So the wording of the conclusion, first of all, break it down into these 4 parts. So the first part is give numbers, give evidence, test statistic in relation to critical value, p-value in relation to significance level. Second step, say whether you're actually rejecting or fail to rejecting the null hypothesis. Then the last step, which is in many ways the most important step, can you actually interpret what this means in the context of the research question? But you notice the wording of how I'm putting it across. I'm not sort of saying that it's definitely true or definitely not true. I'm just saying, well, look, based on this evidence, and also we're using 10% significance level, the new method leads to higher mean test scores than the old method. I'm not using wording like the new method is better or worse than the old method or no different. Because of course that's subjective. But based on this, based on the mean test scores, there's no difference between them.